Okay, so I'm just going to be talking about multi-class classification in this part. So the lecture 9, we're definitely going to be going through multi-class classification throughout this lecture, but we might also, I'm going to try to get to TensorFlow as well, which is a little bit disjointed, but it's a good time to introduce both since we talked about stochastic gradient descent last time, these algorithms, it's very natural to implement them in TensorFlow, and we could get some sense of what's going on and why we would want it. So the multi-class classification, this is just a simple extension of binary classification, but there's some somewhat technical details that we need to get through to really understand what to do in the multi-class case. And it really matters from a practical perspective how you deal with multiple classes. Okay, so I'm just going to use the iris dataset throughout this lecture just for illustration purposes. It's a pretty small dataset, but it is easy to plot. So we're just going to be using these two variables, sepal width and sepal length, and some of this code I've listed it here is adapted from scikit-learn's website, example code there. But the basic idea behind the dataset is that there are multiple features about from these different flowers, the irises, and then there's these different samples, and there's 3 different categories for the samples, 3 different species, I think it is, for the samples, and so these are depicted by these colors here. Okay, so there are 2 approaches to multi-class classification. Main approaches to multi-class classification. First of all, what is multi-class classification? So actually there's a subtlety here. So we're going to predict yi, which lies within some set of classes, right? And these classes are mutually exclusive. So in the case of the iris dataset, these flowers can only be one of these species, right? It can't be multiple species. And that's a feature that defines multi-class classification, is that the output is a categorical variable, and that's our yi's. And we're just going to say it goes from 0 to k minus 1, giving k total classes. I like indexing starting at 0 because it's consistent with how we usually do our notation with binary classification, and it also is it's also consistent with Python. And then it also sort of indicates that 0 is going to be special, and when we and sometimes we're going to sort of treat 0 separately than the remainder of them. Okay, so so we're trying to predict this, and I'd like to contrast multi-class classification with multi-label classification. Multi-label classification, there's multiple y's for each sample. So this could be binary y's, in which case you could think of it as a single sample could have belong to multiple classes at once. But in this case, because the classes are assumed to be mutually exclusive, we're going to be in the multi-class classification setting. Okay, so so we want to train binary classifiers and then select a prediction based on these. So that's one approach. Is just to think of this to cast this as binary classification problems. So the problem is that there's a lot of different ways to do this. So one way to do this is to say that we're going to try to train one of the classes against all of the remainder of them. That's going to be the one versus rest setting. Another setting is we're just going to choose 2 different classes at a time, train each class against the other class. Now the issue is that we have all of these different classifiers. We're going to talk about how do we combine all of these classifiers to get one single multi-class classification, because at the end of the day we want a predictor that can take in an arbitrary x and spit out a y, which is a member of these one of these different classes. Right? So that's the first main approach. The second main approach is to train a combined classifier. And particularly, there's nothing stopping us from using a loss that uses the multi-class response, just like our losses for binary classification used the binary response. And we'll talk a little bit about that as well. Okay, so for the 1 versus 1 case, and throughout we're just going to be talking about our favorite linear classifiers. We're going to train our binary classifiers for all class pairs, and that'll return this is a vector, a feature vector, and I'm thinking about the intercept in these couple of slides to make my life a little bit easier. I'm thinking about the intercept as being incorporated into this beta. So we're going to train a binary classifier for all of these beta hat class pairs for j less than k. So you know there's n choose 2 different pairs of classes, and each of those n choose 2 selection, sorry, not n choose 2, capital k choose 2 classes, pairs of classes. We're going to get a different classifier, which in the linear case just means different beta vectors for each pair of classes. The prediction for this classifier is then just going to be y hat is the j. So for a given classifier, for a given binary classifier, it's y hat jk, which is equal to j if beta hat jk transpose xi exceeds 0. So this really should have 3 indices, y, j, k, and I. And then we're really just deciding, is the ith sample more like a j or more like a k, right? And we're using this linear function to do it. Okay, so now we have a bunch of predictions. We have n choose 2 different predictions for every single sample, right, for the xi sample. So now what we're going to do is define the number of pairs that a given class wins. So we're going to do all comparisons and then just see how many pairs this class wins. And we're going to call that n sub j for the ith sample. And then we're just going to predict the one that has the maximum number of pairs that it wins. So you should think of this as each classifier, each of these binary classifiers is like pitting j against k, pitting one class against another. And then they're going to go to war for each sample, and then that sample is either going to go to j or k. And think of that like a game, right? Like a single game of your favorite sports game, like football. That could be either American or European. And then that comparison, that's the win of a single game. And then at the end of the day, we see how many wins did each class get, and then we choose the class with the most wins. That's how we choose what the prediction is for a given sample, right? And then you have to break ties at random as is standard. So this is actually what SVC does in the SVM module in scikit-learn. The one versus rest case is, it says, let's take every class and think of all of the other classes combined as another class, as class -1, as the negative samples. And then we can train just k binary classifiers. Instead of k choose 2, it's just k choose 1 binary classifiers. Then we get a prediction, a different prediction for every single class, right? But now the issue is that there's no obvious way just from the predictions how to choose them, how to choose what the final prediction is, right? But with a linear classifier, and with any classifier with a decision function, with an output, with a real output, we can then say, well, which one has the largest decision function, which is this beta hat k transpose xi. So we get a bunch of different beta hats. We have k of them, and we just choose the one with the largest. So this should be an argmax sub k, not an argmax sub j. We choose the one with the largest beta hat transpose xi. And again, throughout the intercept is incorporated into the betas. Okay, so in the 1v1 case, the basic idea is that we're going to train binary classifiers for all class pairs, beta hat jk. So I just jumped back to correct some of these typos. Sorry, there was a bit of a pause. So in this 1v1 case, I've introduced 3 indices like I mentioned, and this should clarify things. So y hat for I, there's a different one for every n choose 2 jk pairs. So there's a different prediction for every jk for each I. And then for each I, we look at each j class and see how many of these games it won. And then the predicted class for the ith sample is the argmax. And then for the 1v rest case, I corrected a typo here. The y hat I is the argmax over j of beta hat j transpose xi. So there's only k of these classifiers, and then we're going to choose the one with the largest decision function. So if you're using scikit-learn, you can implement this using a linear SVC for support vector machines, and then use the multiclass equals OVR setting. So this also is in scikit-learn for linear SVMs. So let's talk about multiclass training. So what's stopping us from using a multiclass loss? So a loss that actually takes in the multiclass response instead of thinking of these as binary, a binary response, or separate binary classifications. So there's nothing really stopping us from doing this. For SVMs, it's a little bit subtle exactly how we make this modification. So you can imagine the way that we could do it is we have a bunch of different hyperplanes, and this is in general how we're going to do it for linear methods, is we have a lot of different separating hyperplanes or potentially separating hyperplanes. But then how do we deal with slack variables? So each of them has a different beta, a different intercept. It's important with ridge regression or with ridge terms like this to separate out the intercept, because typically we don't penalize the intercept. So for the SVMs, this requires a modification of this maximum margin problem. Particularly, we introduce these slack variables, but these slack variables have to hold for all of the margins, not just for the single margin. So the basic idea is we want to get it on for every single possible margin. We want it to be on its correct side of the margin, and so that means that this equation holds for all j. That's not the true class. If it's the true class, then it doesn't matter, right? So we have this. This is how much do we have to add to the decision function to get it so that it's to the decision function so that it's on the correct side of the margin. And the basic idea is that you have two hyperplanes, one for each class, and then also the true class, right? So for a given class J and for the true class Yi, we can just think of the comparison between that class and the true class as just a single hyperplane. Because we're going to choose the hyperplane for which the decision function is closest to it, where the coefficients for the hyperplane are just the beta sub yi minus beta j, and the intercept also is similarly computed. It's beta yi 0 minus beta j 0. So this is sort of like you can always remove a single vector and the decision functions, their relative performance won't change. So for example, we could do that for all of the j's that are not equal to yi. And then this positive part is going to be, this should be the max over j not equal to yi. And then you have this is your hinge loss, your new modified hinge loss. Okay, so I just made this correction for the hinge loss. Okay, so for logistic regression, the story is a little bit simpler. So it's very easy to explicitly just create a multinomial model. So before we had binary response variable and we had just a Bernoulli trial for each sample I. Now we're going to think of it as a multinomial trial where it has size 1. And the main assumption is that the log ratio of probabilities is still linear, right? So the log of the ratio of the probability of y being 0 versus y being k is just assumed to be a linear function. Then consider the probability of a given class is going to be the probability that y is equal to k, given x equals little x, is going to look something like this. Okay, I just corrected yet another typo, so I just had this k and the 0 reversed here. But yeah, you can convince yourself that the probability of a given class now, conditional on x, of y being a given class, is equal to the following forms here. So this is similar to what we saw with the binary classification setting. This is the inverse. This would be the inverse logit in that case. Sometimes we call these the logits here because it's log odd probabilities. And so the negative log likelihood, which this is also called the cross entropy, can be written in the following way. So it's the negative of the sum over the classes of the log probabilities of that class times this indicator that y is equal to the class. And so, you know, to get the full log likelihood, you would have to sum this over all I. But this is the basic form, and you can sort of think of it as if I created a vector of these indicators where each component corresponded to each class, then this is like the inner product between the log probabilities and that vector. That's one way to think about it. One connection that's important here, especially when we move to neural nets, is through the softmax. So for numbers alpha 1 to alpha n, m, the softmax is defined as the following thing. It's sk, which is equal to the exponential of alpha sub k, divided by the sum over the exponentials, sum of all the components. So the basic idea is you could take a vector of alphas from 0 to m, and then take their softmax, which makes it so that you first exponentiate them, and then you make sure that these numbers will sum to 1 by normalizing them, by dividing by the sum of the exponentials. That's the definition of the softmax. And so if you let alpha k be the logits here, and then also alpha 0 be 0, so that's for all classes other than 0, and then let alpha 0 be 0, then you can find that this probability is the softmax function applied to those alphas, to those logits in 0. And we can pretty much always get that alpha naught is equal to 0 in some sense, that the first logit is equal to 0, because if it was non-trivial, if it was non-zero, we could just subtract it from all the alpha k's and still get the same softmax. So as a brief exercise, I want you to suppose that your prediction rule is simply the maximum estimated conditional probability. So this is, now let's think about prediction. That's been a little bit about the model itself. So we're going to predict just with the one that has the highest probability. Now we want to simplify these rules. I want you to give me a simplified rule in terms of the beta vectors and the x. Right? So take some time to do that. I'll see you soon.